All right, AP Calc section 6.3, day number 2. Okay, so just a review of where we came from in day number 1. We spoke in day number 1 about the disk method. And the disk method is a method used to find a volume of a revolution which creates a cross section which is circular. Okay, so if this were the cross section, let's say this red dot here represents the axis of revolution. For example, if I took a function here, f of x, and I revolved it from, let's say, a to b, around the x-axis, then this red dot would be the x-axis, right? So if I was standing over here, and hands on the old hips and look in this direction, the cross section that I would see would look like a circle. And it would look like something like that. Okay, so this cross section has a radius, right? And the solid that's created is a full circle. Okay, so this radius here actually ends up equaling f of x, right? So that the radius changes. So here it's whatever f at a is, and then f at a plus some delta x, and so on and so forth. So even though f of x changes, we can still use this method, this disk method, because this solid is created as we revolve, right, our space, our region about that x-axis. So it creates a nice solid space. Okay, so to construct this volume, we would take the integral from a to b of pi times f of x, which is r squared. So you can see our area function, which in this case, a of x is equal to pi f of x squared. Okay, and that yields us a volume, right? A volume of revolution in this case. Okay, so in day 2 here, that was a nice little overview of day 1. In day 2, what we're going to do is we're going to be using the washer method. Okay, so what is the washer method? The washer method is related to a geometrical shape called the annulus. I think I spelled that right. And the annulus looks like 2 concentric circles. So concentric circles have the same center. So imagine that this space right here is an empty space within this cross section, okay? And here's our axis of revolution. And so really what we're accumulating is this blue area. So as we revolve, there's a hole in the middle of the space. That means that we've got 2 functions that are formulating the region that's being revolved. Okay, so what could that potentially look like? And then we'll look at our example here. That could look like this. Let's say I have f of x. Again, that special general f of x. And then let's say I have g of x. Let's say g of x is just something simple and linear. And I want to revolve the region bounded by those 2 from a to b about the x-axis. Okay, so really now what I'm going to have is I'm going to be taking this space here, right? And I'm going to be revolving that. So if you can imagine, oops, that wasn't very good. Let's go like that. That's better. Oh my goodness, I'm falling off the wagon here. All right, so it kind of does this, right? And you can imagine that g of x, we'll call this g of x, is kind of superimposed beneath the x-axis as well. So if I were to stand right here, oh wow, I almost drew the number pi. If here I am standing, I just drew it again. I'll put the hands on the hips and cover that up and look this direction. What I would see is a circle with a concentric circle inside of it. Now if I stood there, I'd really only see like this. This would be like the radius that I'd be seeing, right? Or the circle I'd be seeing. I wouldn't really see this because I'd see the narrowest values, right? But really we would see that the radius of the inner circle would be increasing, right? As x gets larger, okay? So then really this revolved space would create this thing called the annulus. So how is it that we'd find the area, right, of this function, right, the area function, if you will? Well, a of x would equal pi, what we call big R squared, minus pi little r squared. Okay, so what are big R and little r? I should probably do these in different colors. So big R is the distance from the axis of revolution to the further function, right? So our axis of revolution, if I put that in yellow, would be the x-axis. So the larger the two radii would be f of x. Okay, so big R is going to be f of x. And little r, as you can anticipate, is going to be g of x. So in this case, a of x is going to equal pi f of x squared minus pi g of x squared. Now, a couple different ways you could write that. You could write that as pi times f of x squared minus g of x squared, or the alternative, right? So you could write it either way. Okay, so let's look at this example. That's a little breakdown of where we're headed. It says, consider the region bounded by the curves. When you see curves, right, that may give away that you've got a washer method situation. Okay, y equals the square root of x, y equals 1/10 x, and x equals 4. So I know that these two curves, right, square root of x and 1/10 x, they intersect, right, at x equals 0. Oops. At x equals 0. Okay. I don't know why I wrote that y equals there. How about this? Yeah, let's do that. Okay. And then at x equals 4, well, at x equals 4, so the square root of 4 would equal 2, and 1 over 10 times 4 is equal to 2/5. So they're not equal there, but that's fine. We don't really care. So let's draw a little sketch here. Okay, so we've got the point 0, 0, right? The origin. I'm going to draw the square root of x, and it's not perfect, but it'll work. Square root of 4 is 2. And 1/10 x is going to be, it's going to look something like this. Try that again. That's better. Okay, so this is the region that I'm going to revolve. All right, so I'm going to try to sketch this. That's pretty good. Not bad. And not great. How about that? That's good. Okay. So you can imagine that this green space is going to be revolved around the x-axis. This will clearly be a wash washer, since there is open space within the space revolved, right? So you can imagine that you've got something kind of like that. Okay, and you can see how that cone-shaped open space creates the washer. Okay, so it doesn't ask us to find the actual value for the volume, but we do want to find an integral expression. So let's write a of x. So a of x is going to be pi times the function square root of x squared. Right, so think of this as big R, right? Big R. Well, big R is going to be the larger of the two functions. When I say larger, I mean the function whose distance is further from the axis of revolution. So here's the axis of revolution. Further function is f of x. Well, I guess that's not called f of x. It's called just y equals root x. Then we've got y equals 1/10 x. That's going to be our little r. We're going to square that. Okay, so let's put that as x over 10. Now, we could write our integral expression in a number of different ways, but our volume will be pi times the integral from 0 to 4. Notice that these are your points of intersection, x equals 0. And this isn't the point of intersection, this is just the end of this bounded space, right? Sometimes it's a point of intersection, sometimes it's just a value that's chosen. Okay, and I can write this however I'd like. Really, I could leave it just like this if I wanted to and tag a dx on the end. I'm going to choose to write this as x minus x squared over 100. Now, we're not asked to go any further than that, so you can stop there. But that would be how we would find that volume created by revolving that green space about the x-axis. All right, let's look at another example. All right. Let's take a look at example 4. It says, consider the region bounded by the curves y equals x squared and y squared equals 8x. Okay, this is interesting. Let's go ahead and try to sketch this. Okay, here I've got x, here I've got y. Let's draw y equals x squared in red. So it looks something like this. Okay, there's y equals x squared. Y squared equals 8x. Now, this is interesting. Let's take a look at maybe how we can rewrite this. How about y equals plus or minus root 8x? Okay, so what would that look like? Well, that's going to look kind of like this. Now, when it comes to the bounded space, right, I'm looking at that bounded region. Okay, so let me resketch this, kind of zooming in on just particularly this space, right? Because in part A, it looks like I want to revolve that around the x-axis, and in part B, I want to revolve it around the y-axis. So a couple things I've got to do. I've got to find the points of intersection. Pretty easy here. That'll just be the origin. But how about this point right here? Well, I'm going to set the two equal. Now, I'm going to set just positive root 8x. Okay, because this stem right here is just positive root 8x. Okay, and then of course the lower half of that blue graph is negative root 8x. Okay, so I'm going to set that equal to x squared. And we're going to attempt to find this point of intersection right here. Okay, so likely what I would do here to solve is I would square both sides. So I would get 8x is equal to x to the 4th. Okay, bring everything to one side. That'd be x to the 4th minus 8x. I'm going to pull out an x. That leaves me with x cubed minus 8. So it tells me that these functions are equivalent, these functions intersect at two values at x equals 0 and at x equals 2, right? Okay, so this is the value x equals 2, and if I plug in a 2, I end up getting a 4 out. Okay, so I'm going to utilize, at least in part A, I'm going to utilize the x values from 0 to 2. In part B, I'm going to utilize the y values. I'm going to go from 0 to 4. Okay, so let's do some work here. Set up our area function. So our area function in part A is going to, this will be a washer method. It'll be pi times the upper function, which is square root of 8x squared minus the lower function in this case, which is x squared, and we'll square that. So the volume, when we revolve this around the x-axis, will be pi times the integral from 0 to 2 of 8x minus x to the 4th dx. So let's do a little algebra here. Do some integration. That would be 4x squared minus x to the 5th over 5, evaluated from 0 to 2. We'll do some work. That would end up being 16 minus 32 fifths, and then of course minus 0 minus 0. Okay, so our volume, would be, 16 times 5 is 80. 80 minus 32 is 48 fifths. So our volume of revolution here would be equivalent to 48 pi over 5 units cubed. Okay, now let's revolve this around the y-axis. Okay, so in order to envision revolving this around the y-axis, now instead of having a of x, I'm going to have a of y. Now my functions in terms of y that are further from the y-axis, right, or my function would be this function y equals x squared, but I can't use y equals x squared. I have to convert it to x equals plus or minus y. Plus or minus the square root of y. Okay, so what we need to determine is this stem of this graph right here the positive or the negative? And actually it's the positive, right? Because when we consider a function, like an upper function, when we're integrating with respect to x, we think of which function has larger y values. Well, when you integrate with respect to y, you think which function has larger x values. Therefore, that half of the graph has larger x values. So when we integrate with respect to y, in this case, our area function will be pi. Larger function will be big R. So in this case, the larger of the two functions in this quadrant here, right, bounded by the values 0 up to 4 now, right? We're considering y values. It's going to be the red graph, which we would call the square root of y. We're going to square it, and we're going to subtract this function in terms of y, which we had originally, okay, which was, let's write this as x equals y squared over 8. Okay, so that's going to be the function in terms of y. Let's write that here, y squared over 8. Let's square it. Okay, so there's our area function. Now again, our volume is going to be calculated by multiplying pi by the integral from, in this case, 0 to 4 of y, that's y, square root of y squared, minus y to the 4th over 8 dy. It looks like it wants us to do some algebra here. Let me make sure I did that correct. That's incorrect. I made a mistake algebraically. This should not be an 8. It should be a 64. This is going to get messy. That's lovely. So our volume will be pi y squared over 2 minus y to the 5th over, is that 320? Let's see, 64 times 5, 320. Okay, evaluated from 0 to 4. Okay, let's see what we get. 4 squared is 16. 16 over 2 is 8. 4 to the 5th, I believe, is 512. 4 times 4 is 16, times 4 is 64, times 4 is 256, times 4 is 512. No. 1024. Okay, so 1024 over 320. Minus 0 minus 0. Okay, so I may have cheated and looked at my calculator. But what we end up getting here is pi times 8 minus 3.2. And thus, this volume of revolution comes out to be 4.8 pi units cubed. All right, outstanding. Let's look at one more example here. Okay, example 5, last example for this day's notes. Consider the region bounded by the curve x equals 4 minus y squared and the y-axis, and revolved around the line x equals -1. Okay, so now we're not revolving around an axis that we're typically used to, like the x-axis, y-axis. We're going to be revolving around some other, in this case, a vertical line. Okay, x equals -1. So let's draw a general sketch here real quick. Okay, so I know my curve, right, this thing. And the y-axis create this space, right, this region. So here's the y-axis. Now, what does this curve look like? Well, what this curve looks like is a half circle, okay, a half circle with a radius of 2. I'll explain in a moment. Okay, and it's just on the positive x-axis, okay, so it's not on the negative x-axis. If I were to throw a negative in there, you would see, the other half of the circle show up. Okay, and what I want to do is I want to revolve this thing around the line y equals -1. So you can imagine, right? You can imagine that I've got some open space right here in between the y-axis and x equals -1. Okay, so here's the region that's bounded by the y-axis and this function. So let me explain how I got that right half circle there, so that it's not a total mystery. And again, this should not be a negative, that should be a positive. Okay, so let's just square both sides of this thing, and let's add y squared. And I'm going to write 4 as 2 squared. Now this should ring a bell. This is the equation of a circle with radius of 2. Okay. Now, because this radical is positive, I'm considering, all x values that are positive. So there you have it. Okay, so that's one way to help you algebraically to kind of analyze what the function looks like. Okay, so what I want to do and what I'm going to create here is, and this might be hard to imagine at first, but I'm going to be creating this almost, I don't even know how to describe this space. How would you describe this space? Like an apple that's had its core kind of plugged out of it. Right, so you can imagine that this is entirely open. Right, so if I were to, take some like apple coring device and shove it right down in there, there'd be a nice big hole there. Okay, and the radius of that hole is going to be the same all the way through. Okay, so let's set up our area function. Now our area function will be in terms of y. But since we have a washer happening here, we have to be pretty careful. Okay, so let's consider big R and little r. And of course, big R is the function that's furthest from the axis of revolution. So let me pick a color I haven't used yet. How about purple? Of course, we know the yellow line, vertical line, is our axis of revolution. Our big R will be the function furthest away from it. Okay, so let's consider what this really is. This is f of y, right? The distance from the y-axis to this red function right here, right, is going to be x in terms of y, which is this. And then I'm going to add 1 to it. So I'm really taking this function x minus a negative 1, right? I'm adding 1 to it. So that's going to be big R. So I will have, let me start here, pi times big R squared minus little r squared. Now let's talk about little r after we fill this in. Okay, so big R is going to be x in terms of y minus a negative 1. Okay, so what would x in terms of y be? Well, that would be square root 4 minus y squared minus a negative 1. So we're going to square that. That's going to be big R squared. Okay, so we've got pi times that minus, okay, little r. Let's talk little r. Well, little r ends up being, oh gosh, another color I haven't chosen yet. How about, I don't know. I don't have another color. Okay, orange, I guess. Little r is always going to be this length, right? Which will always just be 1. Okay, so I'm just going to square, and I could say technically this is 0 minus a negative 1, right? Because we have y equals 0 here. Excuse me, that's wrong. How about x equals 0 here, right? So I would get 0 minus negative 1 just comes out to be 1. Okay, so there's our area function. Let's clean that up slightly. Okay, it's asking us to find the volume, so we do have to do the work here. Okay, so what would I get if I squared big R? Well, I would get, that would be square root of 4 minus y squared squared, which is 4 minus y squared. Okay, plus 2 square root of 4 minus y squareds. And then plus 1, right? So I expand that, and I'm just going to subtract 1 squared, which is 1. So clearly we'll see that the 1's will drop. Okay, so my area function in terms of y ends up being the following. Pi 4 minus y squared plus 2 times the square root of 4 minus y squared. All right, there's our area function. Now what we're going to do is we're going to revolve this. I'm going to pull my pi out here, revolve it around the y-axis. Therefore, I'm going to integrate from negative 2 to positive 2. Okay, so this is kind of interesting. This is a symmetrical function about the x-axis. So if you wanted to, you actually could do this. You could take 2 times the integral, pi times the integral from 0 to 2, right? So since the 2 halves of this are the same, you could use that symmetry method, but whatever, I digress. Let's continue. So I'm going to integrate 4 minus y squared plus 2 times the square root of 4 minus y squared dy. And at this point, I'm actually going to cheat here, and I'm going to use my calculator. You could, let's see. Yeah, you could work through this and do the algebra, but I'm going to, again, take the cheat method here and use my calculator. So let's type this in for y1. I honestly don't know if the intent of this problem was to do it algebraically or to use the calculator, so let's just do it. Okay, so using my calculator, I end up getting an area of 72.9 989 units cubed. All right, guys, and I did confirm the other way as well that this volume comes out to be exactly the same. So that symmetry idea does work in this case. Not in all cases, but in this one it does. All right, guys, that's it for day number 2. We'll be back in day number 3 with cross-section volumes. We'll see you in the next video.